Okay, so this video is basically a video on concept generation, um, and it's basically going to outline the process that I use personally to come up with designs and stuff. So you might be struggling to like piece an idea together or to even generate a concept. So yeah, this is just to help with that. There are many different ways of going about concept generation and stuff, and if you found something that works for you, then by all means carry on with that. But it can be pretty overwhelming to try and like put a big design together or to come up with ideas for designs and stuff. So this is just to help with that. And also don't be limited by what you see. So it's very easy to like maybe look at my design because I'm going to draw everything, right? So you might look at my design and think like, oh, this is the only way of doing things. So don't limit yourself. Try and find inspiration elsewhere. And yeah, don't limit your creativity. But also don't over, what's the word? Don't, not really over engineer, but like keep your design simple. You don't want it to be like too extravagant, if that makes sense. So it's always better to like think of a really, really extravagant idea and then simplify it than thinking of a very basic idea and trying to make it more extravagant, or like better. I think I'm not too sure of that one, but like I feel like it's harder to like think outside the box, especially when you've like seen a lot of different designs that are pretty similar. You kind of limit yourself. So by all means, don't limit yourself. Try not to. Okay, so this is going to relate to the project that we have where we're designing the funicular. So when designing the funicular or whatever, try and break everything down, right? So for example, we need wheels, right? So okay, cool, you draw a wheel, then we want to connect two wheels together. Maybe you want to connect two wheels together, so then you're going to connect that by a shaft. So yeah, that's typically what's done in most designs. You connect two wheels by a shaft. It's very ugly, but anyways, but you might think, okay, I don't want these two wheels to be connected together, I want them to be independent. So cool, we have one wheel and then another wheel. They're in line with each other, but they're not connected. So okay, if this wheel is spinning by itself, then it's going to need to be attached to the funicular somehow, right? You can connect it via a shaft, right? So you have like a little shaft, so each wheel gets its shaft, I guess, and this shaft will be connected to the body of the funicular, right? So already you've designed the system for which the wheels will be connected to the thingy, to the funicular. So for this design over here, we'd need to attach the wheels to the body of the funicular somehow. At least with this design over here, we know that, okay, we can attach the shaft to the funicular at this point over here and at that point over there, right? And then again at this point over here and at that point over there. Okay, then for this design over here, there's multiple ways of attaching it, right? So we could maybe attach it in the middle. We could maybe extend the shaft out and attach it on the sides if we wanted to. right? There's many different ways of attaching it. So I guess kind of to recap, we first started off with wheels because we know our design is going to have wheels. And then from there, we figured out, okay, are the wheels going to be connected? Are they going to be separate? And then we asked the question, how are we going to connect the wheels to the funicular? Okay, then in connecting the wheels to the funicular, we actually need like a practical way of doing it now. So we've basically blocked out the general shape of how this is going to look. Now we want to actually make this design functional. So we want to like actually make it work, right? So in this design over here, in this design here, at each attach point we're going to need bearings. So we're going to have a bearing here, and we're going to have a bearing here. Okay, and then at this point over here we're going to have a bearing here, we're going to have a bearing there, right? The reason why we need bearings is because it's going to allow the wheels to spin without the frame of the funicular spinning, right? So it allows relative movement between the wheels and the frame. Okay, so if you think about, let's say I have a beam for the frame of my funicular, and then I have a shaft that's connected to it, and then I have the wheel connected to that. If the wheel were to rotate and there was no bearing, or if there's no bearing in the shaft here was directly connected to this beam, then the beam would also rotate, right? But we don't want that. We want the beam to stay stationary while the wheels rotate. Well, we want the beam to like move forward, but in order for that to happen, the wheels need to rotate, and this must stay stationary. And in order to do that, we can put a bearing, right? So the bearing will allow the wheels to rotate without having the frame itself rotate. Okay, so we need to put bearings in these locations, and to do so we'd need some sort of bearing housing or something to contain the bearing, basically. And the reason why you'd need that is if you look at your frame, so your frame will probably, you might use I-beams, you might use all these different steel sections. So let's say we do use an I-beam for our frame, right? Let's say we do use an I-beam, then you'll notice that the web is really thin, right? So this web over here is very, very thin. So if I draw it like that, you can see it's pretty thin, and my bearing is going to be pretty thick compared to the web. Okay, so I won't be able to place my bearing inside here comfortably. It's going to be sticking out kind of like that in most cases. And also what I'm scared of is introducing stress concentrations into my frame, right? So the frame in most cases takes the brunt of the load. So it takes the most load for your structure. So you want it to be free of stress concentrations as far as possible. Obviously, you can design in such a way that it can take those stress concentrations, but you want to kind of minimize it, especially in the beginning stages where you don't really know what direction you're going to take. So let's try and come up with something that will hold the bearing and let's try and minimize any damage we'll do to the I-beam. So we don't want to really drill holes. We want to try and avoid that for now. Let's try and have something that we can weld onto the frame, for example. So we basically want a box. So I'm drawing a box just because it's a very simple shape. This box must house my bearing, and the shaft will fit into the bearing. Let me draw the bearing in a different color. So this will be my bearing, and then the shaft will fit into the bearing, and then it's going to extend outwards, right? And then my wheel will be placed over the shaft. So this is the wheel, then this is the shaft. This isn't to scale, by the way. The wheel would need to be a lot longer than the frame itself. So if this is the ground, the wheel would actually need to touch the ground. But doesn't matter for now. So just as long as we can visualize it. This is our bearing. So cool. We have this set up, and if the shaft were to rotate, then as long as the wheel is like sort of press fit into the shaft, or is like fit tightly onto the shaft, then the wheel will rotate along with the shaft, right? So the shaft is rotating, the wheel is rotating, and then our bearing, the inner race of the bearing, will be rotating. So if I draw a little bearing here, and have that, so the shaft is fit into this section over here, so the inner section would be rotating, but the outer section would be stationary, right? And then that's basically what we want. So this design would work for what we needed to do. So let's go ahead and try and design this bearing housing. So basically we need the outer portion to fit the outer diameter of the bearing, so this outer diameter here, and we might have a situation where the shaft is slightly longer than the end of the bearing, so we might want to accommodate for that. That's completely up to you. It's always good to accommodate for that, just so that your tolerances can be pretty loose and stuff, and also because of thermal expansion and all that stuff. It's always good to like include gaps where you can. So our bearing seat or housing, I guess, would look something like this. So over here, this little compartment here would seat the bearing, and then you'd have a little section that will allow for the shaft to stick out a bit. So let's draw the shaft in. You're going to have something like that, and then the bearing's going to have a press fit there, so it's going to be pretty tightly packaged into this little container, I guess. And then this is basically a section view of the bearing housing. Okay, so here you have your bearing, and then over here you have your shaft, and then this is your housing. Cool. So we've basically solved one of our problems, which was allowing the wheels to spin without having the body spin, right? And to do so, we had to create a bearing housing. So if you're choosing this design over here, your bearing housings will be located at these 2 points, right? And then if you're choosing this design, your bearing housing will be located at these 2 points. So yeah, there's many ways of going about it. You could, instead of creating like a bearing housing, you could maybe have the shaft attached directly to the frame. So in that case, let's draw the frame as a square, and then the shaft will be directly attached to it, right? And then we want the wheels to spin freely from the shaft over here, because the shaft is directly attached to the housing. If the shaft were to rotate, then the housing would rotate as well. So pretend the shaft is welded to the housing, then we'd want the wheels to now rotate freely from the shaft, and we can do so by putting in a bearing. So we just put in bearing inside, in between the wheel, right? And this is all going to depend on what you choose to do, and also like what kind of wheels you're choosing, all of that kind of stuff. It's all going to depend, right? Yeah, so you might find benefits for choosing a design like this. So a design like this would how would it be better? It might be easier to align everything. Would it? Sort of. Okay, yeah, I don't really know which one is better, but yeah, they're both ideas. I'm sure one of them is better than the other, but you can weigh that out yourself and decide which is better. I will say though that the longer the shaft is, then so the longer the shaft that connects the two wheels together. So you can see in this design, the shaft is pretty long compared to in this design here. So the longer the shaft is, the harder it will be to line everything up. And you can't have wheels that aren't concentric. So for example, I don't really have an example, but if these two wheels are misaligned, then it's not going to run very smoothly. You're going to have a lot of vibrations, which you don't want, right? So one very easy way to mitigate any misalignment is by making it shorter, so that when the people are manufacturing it and assembling everything, it's less prone to human error, and it's a lot easier for them to do. So you might find that this design is a lot easier to assemble compared to this one, but it doesn't mean that this design here is impossible. Still probably possible. It's just it might be more error prone compared to this design here. And then another thing you can do to kind of mitigate alignment issues is try and make self-aligning components, right? So, or components that help you align two things together. So for example, this bearing housing, you can put a taper to help align the shaft. So you can specify that the shaft at the end should be machined. So you're already going to have to machine it so that it fits into the bearing nicely. So why not add just another quick operation to the machining so that it tapers. So you're going to have a taper kind of like that, and then the shaft will perfectly fit into this taper, kind of like that, if that makes sense. And then you'd have your bearing over here. Okay, so if that's the case, then the shaft would be perfectly aligned with the bearing housing, allowing it to be perfectly aligned with the bearing. And then if you have a second bearing housing, you just need to make sure that the two are aligned on the same spot of the beam itself, right? So maybe on your beam itself, you specify that there must be plates or something, or like, okay, honestly, I don't think you need to think this far, but like, do consider the alignment of things and like try and make it easier. But I think I was overcomplicating it. Anywho, so the bearing part, hopefully you get the bearing part. Let's scrap all that, forget that. So we did the bearing housing, cool. We did the wheels, so you can choose between your wheel design, and also don't be scared to come up with your own design. So then the next thing we need is the wheels to connect to something, and that something is going to be the frame, right? So you would then design the frame according to how you're going to like place stuff on it, right? When designing the frame, I wouldn't say consider things like flooring and stuff as yet. Maybe if you're going to put seats and stuff like that, don't consider it for now. Just consider the main structure, the main shape that your funicular is going to take, right? And start from the bottom, then maybe think of like putting flooring in the walls, and then afterwards you can think of things like doors, roofing, stuff like that. So for example, let's say we wanted our frame to have the shape of a basic rectangle, right? And let's say that you wanted to carry your pipe in this manner, right? So you wanted to carry it like that. Cool. So the issue that you're going to have, or rather the parts of this that would need to be really strong, are any parts that run from here to here. So any parts that run this way. So if you were to think of them kind of like that, then they would kind of bend down because the pipe is really heavy, right? So any structural supports, you'd put them lengthwise, right? So we'd have a piece like that, and then we'd have another piece like that, right? And then we obviously need to join these two pieces together, and also the side also has to be pretty strong. So we're going to join it like that. So these are all the same structural member. So if you're going to be using I-beams, then these would all be I-beams or whatever. So we're just going to assume this shape for now. Remember, these can be whatever you want. Doesn't have to be square tubing or whatever. You can use literally any steel structure, and I recommend looking at steel catalogs and stuff. I don't know if the red book, it should have like different steel structures, but I haven't read through it. A quick and easy catalog to look for is Max Steel. You can look at Max Steel and see if you can find any steel sections to use in your design. Okay, but don't try and choose shapes now. Just get the general layout first, and then from there, once you have your general layout, you can start doing basic load calculations and then choosing shapes from there. So with this design, you're going to need, so we said that structures that run from this point to this point are going to be the issue, because they will take the most load if you're loading the pipe in the center. So we might have to add supports in the middle, right? So we can go and draw those supports in, and we won't know how many supports we need and what material they should be and all of that stuff, but that doesn't matter too much. Okay, for now it doesn't matter too much. Just get the general shape of your funicular down. Okay, so we have these supports in the middle, and then we also have the outer sort of frame of the funicular. Another reason why you'd want supports in the middle is if you're going to have some type of flooring. So if you're going to put a floor, like let's say you put a big steel sheet as your floor, what's going to happen is that sheet is going to kind of sag in the middle. So in order to prevent that, you need to put supports. Okay, so the supports are going to help with that, and prevent the floor from dipping down, and it's also going to give the pipe itself more support. You also have to remember that the pipe will tend to bend under its own load, under its own weight. So in order to prevent that, we also need supports for that. Okay, and then these supports will help with that. Cool, so we have the supports in, and let's kind of make space for our wheels. So let's say that we went with this wheel design. Okay, so we're gonna have a little box for our bearing, right? This is our bearing housing, and then coming out from there is going to be the shaft, just a tiny portion, and then you're going to have the wheel, and then you're going to have the rest of the shaft that goes there. Then you're going to have the rest of the wheel, and then you're going to have the other part. So So you are the bearing thingy, and then you're going to have the rest of your shaft. So you have two bearing housings at these locations, then you have your wheels, and then you have the shaft that connects them in the middle. Okay, cool. So obviously this is also going to be over there, but I'm just going to draw it in one location. So we have the basic structure for the frame of the funicular and the wheels as well. Alright, cool. So let's just do a quick sanity check and see whether or not our design is viable, right? So our pipe will weigh about 5 tons. So that's 5,000 kgs. Okay, converting that to newtons, it's going to be pretty much 50 kilonewtons. Right, if you treat gravitational force as 10, right? Then let's make the assumption that each of the bearings will take a quarter of this load. So we're going to have, in total, we're going to have 4 bearings, right? So 1, 2, 3, and 4. And then let's assume that they're going to take a quarter of the load. So 50 divided by 4, that's 12.5. Okay, so each bearing takes 12.5 kilonewtons. Okay, roughly, right? Might not actually take that much. You'd have to go and draw a proper free body diagram, but assuming that each bearing takes this amount of load, we can go look at a bearing catalog and see if there are any bearings that can actually take that amount of force. And then from there we can see, okay, can we continue with this design, or will we have to change the layout of stuff, right? And from a bearing catalog that I looked at a while back, there's bearings that can take up to 26 kilonewtons. So this is viable. Our design is viable. So in the case where we weren't able to create something that could take this amount of force, right? Let's say that this load was way too much for the bearings, and there weren't any ones on the market that could take this force. We could very simply just add more bearings to take the load, right? So you could maybe add another set of wheels in the middle, right? Something like that. Or you could add a bearing in the center. So you'd add a bearing here in the center, and then you'd attach it to the frame somehow. So maybe this bearing housing is attached to this part of the frame, and then you do the same over here, where you'd add another bearing housing and attach it to the frame. So obviously you don't really want to incur additional costs if it's not necessary, right? So you don't want to buy more bearings than you actually need, right? And also, if you're going to be attaching your bearing to this frame over here, then you might have alignment issues. So if this portion of the frame is not perfectly perpendicular to this portion, then you're going to have alignment issues. I'm not too sure if we're needed or required to consider things like alignment issues, but it's always good to think about. But yeah, So since our design works, we can continue onto things like the 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 wall, I guess, of the funicular. So it's gonna depend as well on how you're thinking of designing it. So is the pipe gonna kind of stick out a bit like it is here? If it is, then that's obviously gonna affect how it's gonna affect how the wall looks and how you accommodate that. So how are you gonna accommodate that? How are you gonna have let me use this. Are you gonna have the wall be kind of like that, right? Are you gonna have a circular cutout, right? Is the wall gonna help like prevent it from sliding in this direction, right? So all of those little considerations you'd need to do, but do it step by step, right? So we've done a step by step design, and we've got up to this point where we have the wheels and we also have the frame. Then from there we can design the flooring and then also methods in which to attach the pipe or to hold the pipe down, right? And then in your methods for holding the pipe down, don't just consider the horizontal case, also consider the case where it's at an incline, right? And then one thing the lecturer said is that if you design for a perfectly vertical case and your design is viable for that perfectly vertical case, then you'll never have a problem with the incline case, right? But how likely is it for your funicular to be in this position where it's perfectly vertical? Chances of that happening are more or less zero depending on your design, but I would assume it's pretty much zero. So yeah, I would say design for a steep enough angle. Yeah, and the angle at which you design for and all of that will come from research. Yeah, I hope that kind of makes sense. And I hope the design process is a bit easier. So just to recap, we started off with saying that the funicular needs wheels, and then we discussed ways in which we can configure those wheels. So we could put a shaft in between the two wheels, kind of like this design here, and then we could have the wheels spin independently, right? So kind of like this design. And then we went on to we broke down the wheel design further, and then we said that we needed bearings at these locations, and then we also needed a bearing housing at those locations, and we said that that bearing housing will attach to the beam or the support for the housing. So we designed a little bearing housing over there, and then we also discussed a different method of placing the bearing, or like placing the bearing in a different location. Could place it here. So hopefully from that you can see that there's a lot of freedom in your choices, and yeah, it's all going to depend on what you choose to do. So don't limit yourself. And then from there we discussed making a frame. So we just drew the simple shape of how the pipe would be supported. So have a flat platform, and then from there the pipe sits on top. And from there you need to identify which members will carry the most load or will be more susceptible to fail, and then you strengthen in that direction. So from here to here, right? And then from there we placed our supports in that direction as well. And then we also discovered that these supports will also prevent the floor from flexing, which we don't want. So it will also support the floor that we will decide to place later. And then cool, I hope that makes sense. When doing your concept design, you don't really need to do load calculations as yet. I personally just like to do it so that I can see that my design is going to work. It also makes the later processes a lot easier, provided that I choose my own design, right? But also in the process of doing your concept design, critique your design. Don't just design and think, okay, this is going to work, this is going to work. Think of things that could go wrong with your design, right? So for example, with my design, with this design over here, we don't know if the wheels are going to be large enough to lift the funicular up, right? So if I chose to put I-beams on the side, right, I won't know if so that's the bearing housing, and then that's the shaft, and then this is the wheel. So let's say this is the biggest diameter of wheel that I could find. There's still going to be a gap in between here, so the wheels aren't going to really touch the rails, or the wheels are going to touch the rails, but I'm going to have a portion of my frame that's lower than the wheels. And do I want that? Do I not want that? So cases or like reasons why you wouldn't really want that is if there's like a rock or something in front of your funicular, then the frame is going to hit that rock, right? So in most cases you would probably want the frame to be above the wheel, so you'd want something like that where the gap is kind of in the opposite direction, so there's like some clearance between the ground and your frame. Okay, so that's one critique I have with this design. So think about critiques for your design. Don't be one-dimensional and just think that everything's gonna work. Think about ways that it could fail and stuff like that, and then that will help you with your subsequent processes. Calculations aren't really needed for the concept design, but it does help bring up potential issues as well. Another potential issue with this design is if the pipe is hanging out, right, then how are you going to secure it from moving in this direction? So you need to kind of think of something like that. And if you aren't able to think of a solution to that, then you would probably say, okay, we just need to like push it down really, really, really hard and hope that friction keeps it from sliding sideways. And that's could work, would probably work, but it's not really the best thing to do. Prof did say, is it Prof? I don't know. Dirk did say that you want to avoid friction for securing things. So I hope that helps.